Welcome to July 9th LeetCode Challenge, longest increasing subsequence. Given an integer array nums, return the length of the longest strictly increasing subsequence. A subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. For example, 3, 6, 2, 7 is a subsequence of the array. Here you go. Alright, so example 1. So we have an array nums here, and we want to find the longest increasing subsequence. So they give you the output as 4, being the longest subsequence being 2, 3, 7, and 101. So we basically have to remove or delete, or we don't have to, find the longest increasing subsequence within nums. That's pretty much the idea. And there's a trick here to figure out how to do it n log n times. So we'll go with the first instinct / the most naive approach to this would be the realizing this is a dynamic programming question. So if we were to do this just regular straight up, there's two things we need to know. First is we know that we have to find the maximum of the longest increasing subsequence, and also we want to know that the decision is going to be based on our previous decision, right? So we have to roll out some other alternatives. So in order to do that, we're going to initialize a DP array with the length of nums here, and then we're going to do a nested for loop for element I and j within, and then we're going to find whether the element of I is greater than j. If it is, put it into our dynamic programming array and then return the maximum that we get from it. That's pretty much it. Let's kind of code it out and see how it goes. We initialize our dynamic programming array with 1 because our minimum length of numbers is 1 right here. And we're going to multiply that by the length of nums. And then we have our dynamic programming array initialized. Next thing we want to do is do our nested for loop. So for I in range 1 all the way to the length of nums, we want to run a j loop here. So for j in range, I've got in right here, in range of I, so our nested for loop, what we want to do is if nums at position I is greater than nums at position j, then what we're going to do is we're going to update that to our dynamic programming array at position I. So we're going to build a dynamic programming array if the previous element is larger. Let's see. Yes, if the element previously is larger than it, then we want to make a new dynamic programming array. That's what we're going to do. So if we find the max of dp at I and dp at j plus 1. And then at the end of this, we want to return the maximum array we have from that. Return max dp. All right, let's run this. Let's submit it. See if this works. Since we have two nested for loops, the big time complexity is actually big O of n squared. Because we have two nested for loops, and space complexity is also big O of n. It's big O of n, I should say, because we have to use the relative input size of the DP array, so which is the length of nums. So basically, we initialize the DP array with the length of nums, and then it's equal to 1 because 1 is the smallest we can get here, representing the longest increasing subsequence that we can get in index I. And then we iterate from I1 to the length of nums here. Length of nums. And for each iteration, we'll do a second for loop here to get j in the index of I. So for each, so we're gonna check each element before I. If it's smaller, if it's check to see if j is smaller than I. If it is, then we reassigned our dynamic programming element I to the maximum either I or j plus 1. Alright, then we just return the count of the dynamic programming array as the longest increasing subsequence. So yeah, this is accepted. There you go. However, can we make this a little bit better? Can we make it a big of n log n times, right? Which is a lot quicker. So let's see if we could figure this out. So another way of, I guess, putting making this a little bit better is to think of building a sequence that's not, I guess, like not building as we go along, but we can build it in, I guess, intuitively, not intuitively, a little bit more cleverly, I should say. So let's give, for example, you have an array of elements called, let's say, 8, 1, 6, 2, 3, 10. Say, for example, you have that array, right? A number array. How can we build a subarray from this that's intelligent, that we could have an longest increasing subsequence from this? How do we build this in an intelligent way? So for the first element is 8. So we want to consider that this is the best one option so far. So if we go there, we say, hey, we see 8. This is the only one we have, so it's the best sequence we have. Then move to 1. Oh, it's smaller, so we can't increase the length of the subarray anymore. So it means 8 is less than 1. So what we're going to do next is we have to choose to only keep one element. But since 1 is smaller than 8, we want to keep the smaller one, right? Because it's a wise decision at the moment. So now we have 1 in the subarray. Then what do we want to do next? So we keep on going. Next, 6 is increasing. That's good. So 6 is larger than 1. We're going to keep that. So we have to add that to our subarray. Then we move to the fourth element, which is 2. And 2 is smaller than 6. So hey, we cannot make a bigger array using 2. So what should we do now? Should we keep what we have or start over with a 2? Actually, however, since 6 is larger than 2, but 2 is larger than 1, what we're going to do is delete 6 and add 2 there. Let's just follow me here and see where it goes. Then we move to the next array. Oh, we get 3. So 3 is larger than 2. We could actually immediately add that. Then move it to 10. 10 is larger than 3, so we could actually even add that to the array. And then we get to the end, which has nothing. So we return the count of the length of sub, and then we get 4, which means we're done. So that's kind of how we're gonna approach it, using kind of building our sequence in a more logical way. So here's how we're gonna do that. We're gonna initialize our array called sub, and then we're gonna iterate through the inputs starting from the second element. And then for each element, what we're going to do is that we're going to find if the num we have is larger than the previous number we had in our array. Otherwise, we're going to iterate through the subarray and then find the first element that's greater or equal to the number that we're at, and replace the element. Then we're going to return the length of the sub. Return the length of sub. So let's go about doing that. It's not the n log n solution, but it's going to use that as a template to build upon something better. So we have sub and nums at 0. So building an array of an array with 0. So for nums starting at 1, the next one, what we're going to do is that if nums is larger than the subarray nums at -1 is the last number we have in our subarray, so we're going to add if that condition is true, we're going to append the nums that we're on. Else, if that doesn't work, what we're going to do is find the first element in the subarray that's greater than or equal to num. So in order to do that, we are going to develop, we're going to initialize, we need an iterator. So we're going to iterate through a while loop. So let's say an iterator for I equals 0 while nums at is greater than subarray at index I, we are going to increment I because we want to update our count here. And then what we're going to do is replace the subarray at index I with nums if this is not the case. So num. And at the end of this, we want to return our actual length of the nums of subs, I should say. Sub. Okay, let's see if this runs even. Oh, nums. Is it nums? Num. Why am I calling it nums? Call it n. It's a lot easier. Alright. Oh, whoops, forgot to change this one. For 4, let's submit to see if this works. Alright. So what we have is still a big O of n squared, worst case scenario, because the algorithm is taking the same number of steps as the first approach. However, the average and best case is significantly less because we have this while loop here, not a for loop, but we have a for loop and then a while loop now. So this number actually gets less and less each time, if possible, at the best case, right? And space complexity is storing it in a big O of n times because in the length of subs. So looking at this generic structure now, what we're going to do is we're going to prove this using a binary search. Alright, how are we going to do that to make it n a log n times? So we see we have n times right here, I should say. We have this for loops n right here. What we're going to do is we're going to change the general output of this while loop to make it a log n response. Alright, so what we're going to do is actually erase this to 0. So we have, so same idea. We're going to initialize the subarray containing the elements of nums. But now we're going to iterate through the same thing as before, subs. Otherwise, we're going to perform a binary search on the subarray. So to find the smallest element that's greater or equal to nums and replace that element with num. And then same deal, return the length of sub. So let's see if we could modify this slightly. We don't need to start from 1 anymore. So for n in nums, what we're going to do is that we are going to erase this. We're still going to update sub I with index n. And then sub.append n. Yeah, we still need this. And we are going to define an iterator called bisect left. So we're going to do a binary search on that with using sub and n. So we're going to define this iterator using bisect left for the sub and n. And then we're going to have to update our if statement here. So let's see. So if I is equal to the length of sub, then what we want to do is we want to append n to sub. Because if the number is greater than any element in sub, then we want to add it to it. That makes sense because we want to expand it because it's increasing. Otherwise, we want to replace the first element in our subarray that's greater or equal to the n value. And we update that, and let's run this to see if this works even. Finish. Oh, that's a lot quicker. Let's try this again. Alright, let's submit it. So yeah, so the bisect module actually provides a very handy way to do a binary search in sub using n for us. So time complexity would be big O of n log n, because binary search just uses log n times, and we have a for loop here, which is a linear time, not linear, big O of n, so big O of n times log n time complexity, so it changes dramatically. And the space complexity is still big O of n because it's storing everything in the subarray. Well, that's pretty much it. Nice and short and concise and compact answer. Like it. Alright, have a great day.